Welcome to Standing on the Shoulder of Giants. This programme brings us to the end of part 1 of this series, but never fear, part 2 will be following on very soon, more of which later. In astronomy, we regularly find ourselves asking questions that are so profound they can almost seem absurd. Where did the universe come from? How will it all end? These two questions might seem ridiculous from a scientific perspective, but they're actually very compelling astronomical topics, and physics gives us the tools we need to craft real answers and test new theories in painstaking detail. These two questions are also deeply intertwined. Both deal with what our universe is made of, as well as the physics of how everything interacts, how we see it changing with time, and what lies ahead. In this program we'll tackle what astronomers think of these fundamental questions. When asking questions this big, it's good to start by being very clear on what we mean. So to start, we're going to define what we mean by the universe's beginning and end. In earlier programs we talked about Georges Lemaitre, the Belgian priest and astronomer who first proposed the idea of an expanding universe. He then extrapolated this idea back to the beginning of time, noting that any expanding universe must have expanded from some initial moment or starting point. Years later, the English astronomer Fred Hoyle was describing this theory during a radio interview and summarized it by saying that all the matter in the universe was created in one big bang at a particular point in the remote past. Hoyle himself didn't support the theory at that time, but with that interview he unwittingly coined the term that would go on to define this widely accepted theory of how the universe began, the Big Bang. The Big Bang itself describes the first initial instant, the moment when the universe first burst into being from an infinitely dense and hot primordial point, known as the Singularity. At the instant of the universe's birth, this point began to expand, ballooning from impossibly infinitely small into the beginnings of what we now know as the entire universe. If you think this is sounding a bit like science fiction, or even poetry, that's understandable. The laws of physics themselves make it very hard to us to study that initial beginning point of the universe. However, even in the tiniest fractions of a second after the Big Bang, physics does allow us to begin describing our new and evolving universe. What happened in the moments after the Big Bang to get us to where we are today? When we talk about the beginnings of the universe, we are trying to understand these earliest moments and how they affect what we observe today. You're probably thinking, so, what does all this have to do with how the universe ends? Where we think the universe came from, and how it got to what we see today, matters a great deal when we try to project forward to where it's going. Those initial moments that drove the formation and expansion of the universe will continue to influence the evolution of the universe and its ultimate end. Will it keep expanding forever? If it does, will that expansion eventually rip the universe apart, or cause it to slowly drift apart, fading and cooling into oblivion? Or will this expansion slow down, stop, and maybe even reverse? Will the universe eventually careen back inward in a reversal of the Big Bang, ending in a big crunch and a new singularity? These are exciting and compelling questions, but they are also incredibly hard to answer. Fortunately, astronomers today have the tools we need to develop and test theories to reach as far back as the beginning of time, and as far forward as the end of everything. With cutting-edge telescopes, astronomers can measure how the universe is moving and expanding today, measuring how quickly galaxies are moving away from us, calculating the Hubble constant, and testing whether those data are consistent with a universe that's getting ready to crunch back together or tear itself apart. This might seem strange, because it isn't obvious that looking at the universe today would tell us much about its earliest beginnings, but this is where the speed of light is on our side. Observing very distant galaxies is like looking back in time, since light emitted millions or billions of years ago is just now arriving at Earth. Studying those galaxies' properties and how they move help us to fit the pieces of the universe that we study into a puzzle that changes with time, and studying those changes tell us how the universe has evolved. We can also use this same principle, the speed of light and observations that act like time machines, to peer as far across the universe and as far back in time as we possibly can, detecting light from some of the earliest moments of the universe. The cosmic microwave background is the faint radio wavelength glow of light emitted in the earliest epochs of the universe, and the properties of that background act as fingerprints of things that happened even earlier in the universe's beginnings. By combining these observations and everything we know about the laws of physics, we can begin to answer questions that may have once seemed impossible to address. Understanding the earliest moments of the universe means understanding how we got from the primordial singularity, the seed of the Big Bang, to the vast web of space-time containing the planets, stars and galaxies that we see today. Studying the cosmic microwave background gives us a glimpse of how the universe looked about 300,000 years after the Big Bang. But what about earlier than that? What happened in the first fractions of a second after the Big Bang, and how did that shape the universe as we see it today? This question ultimately led to an innovative new theory that could explain the earliest moments of the universe, proposed by physicist Alan Guth. Alan Guth was born in New Jersey in 1947. A first-generation college student, he left high school a year early to attend MIT and stayed there to earn his bachelor's, master's and doctoral degrees. 6 years later he was working as a researcher at Cornell University, studying particle physics, when he attended a presentation by Robert Dicke. If that name seems familiar, he was the very same person we learned about in an earlier program who had designed a groundbreaking new microwave receiver and worked for years to detect the cosmic microwave background before being scooped by the scientists at Bell Labs. By 1978, the cosmic microwave background had been a topic of study for more than a decade, and physicists like Dicke were beginning to explore inconsistencies between the theory of the Big Bang and the properties they were observing in this light from the early universe. According to the Big Bang theory, the density of the universe, how much matter and energy appeared to be packed into a given space, seemed absolutely perfect. Suspiciously perfect, in fact. The universe was exactly as dense as it needed to be to give us what physicists call a flat universe. One that doesn't crunch back on itself or rip itself apart, but instead smoothly expands. Such a perfect density seemed too good to be true, and it also struck Dicke as odd. Studying the cosmic microwave background had shown him that even the smallest fluctuations in the properties of the early universe would be amplified and show up as big deviations today. This meant that if the density of the universe was perfect now, it must have also been perfect in the universe's earliest moments. If it had deviated even a little bit at those early moments, the universe would look dramatically different today. An analogy might be standing at one end of an enormous tightrope and watching a marble roll perfectly across its entire length. The odds of this happening seem impossible. You would expect even a tiny fluctuation in the rope would upset the marble's balancing act and ruin its progress. A perfectly flat universe, one that had always been perfect and never got disrupted into crunching or ripping universe by early fluctuations. This perfection struck Dick and others as a puzzle, and that same puzzle sparked Guth's curiosity. Another detail of the cosmic microwave background was also curious. Astronomers in 1978 believed that the cosmic microwave background was homogeneous. It looked pretty much the same no matter where we observed it. However, the fact was strange when they thought about it. This light had been emitted in the early universe, and from all over the early universe. Yet different expanses of the universe were completely disconnected from one another. So why did they match so perfectly? This would be like two people shopping for blue paint in different hardware stores in different cities and picking out the exact same colour. Setting coincidence aside, it's impossible to explain such perfect agreement unless the two had been together previously, exchanging information to reach a shared result. For our two paint shoppers, we can bring them together with a big book of colour samples to help them coordinate a plan. But how can we bring different parts of the universe together? By 1980, Alan Guth thought he had a solution to both of these problems: cosmic inflation. The idea is deceptively simple and focuses on the universe in the first fleeting moments after the Big Bang itself. This period of inflation is crucial, but extremely brief. You might be familiar with the mathematical concept of exponents. A number raised to the power of 2 means we multiply the number by itself twice, turning 10 squared into 100. Raising a number to the power of 10 means we simply multiply it by itself 10 times, turning 10 into 10 billion, or a 1 followed by 10 zeros. You can see that positive exponents can increase a number's value dramatically. Negative exponential growth does the opposite, decreasing a number's value and letting us express very tiny numbers. 10 to the power of negative 2 gives us a fraction of 1/100th, or a 1 sitting in the second position after a decimal point. 10 to the power of negative 10 gives us a fraction of 1/10,000,000th, or a 1 sitting in the 10th position after a decimal point. Exponents are crucial for understanding both how brief and how dramatic inflation was in the early universe. We think that inflation began at a time of 10 to the minus 36 seconds, a minuscule fraction of a second after the Big Bang, and it only lasted about 10 to the minus 32 seconds. In that brief flash of time, the universe expanded by a factor of around 100 trillion times its previous size. That's a 1 followed by 26 zeros. This dramatic expansion explains how the universe could have gotten so enormous so quickly, and in doing so it explained why vastly disparate corners of the universe could look so incredibly similar. This rapid expansion would also help suppress the effects of any perturbations in density at these early times, allowing the universe to look perfect and flat today without implying that it had to start and stay perfect in those early moments of the universe. Alan Guth's theory perfectly explained a number of observations, and it agreed wonderfully with the Big Bang model of how the universe began. Later on, work by physicists Andre Linde and Andreas Albrecht and Paul Steinhardt refined this theory, imagining different possible trigger mechanisms that could kick off this exponential inflation and describing how it would stop, with the universe settling back to a slower rate of expansion and beginning to form the first elementary particles and atoms. Inflation is a popular and widely accepted explanation for the earliest moments of the universe, but there's a catch. A theory that agrees with existing observations is very robust and satisfying, but successful theories should also accurately predict things. Put another way, theories can always be modified or fine-tuned by scientists who explain what we already see. But predicting something and then seeing it come to fruition is a much more powerful test of whether a theory is correct. Physicists have argued about whether inflation has truly passed this test. Observations of the cosmic microwave background in the decades since Guth's 1980 publication continue to agree excellently with the theory. However, the theory is designed to explain the cosmic microwave background. Explanations for the trigger mechanism of inflation and exactly how that exponential growth of the universe was driven also remain elusive. Still, there are some possible new tests that could prove or disprove inflation theory. One such test is searching for the gravitational signature of inflation. That early immense expansion of the universe should produce something called gravitational waves, ripples in the very fabric of space-time, and the remnants of these ripples should still be detectable today, affecting the appearance of the cosmic microwave background. In 2014, a team of radio astronomers operating a telescope at the South Pole held a triumphant press conference to announce that they had found this telltale signature of inflation, seeing exactly what they had hoped to see in detailed observations of the cosmic microwave background. However, a more careful analysis quickly revealed that their observations weren't echoes of the universe's earliest moments, but the result of light emitted by interstellar dust in our own Milky Way. While it might sound silly to mistake light from bits of dust for the earliest echoes of the universe, dust is actually a ubiquitous and very challenging aspect of observational astronomy. Tiny dust grains floating through interstellar space can block or deflect light, and even glow and emit light themselves, and they're everywhere. Properly accounting for dust is a challenge that affects almost every subfield of astronomy. Seeing a signal from dust doesn't mean that an underlying signal from inflation isn't there. It just means we can't be sure it's there. As we improve our observing power, we may one day be able to take sensitive enough measurements to search for this signature of inflation and test once and for all whether Alan Guth's theory is correct. Inflation gives us a theory of how the universe began, and observations of the cosmic microwave background give us ways to test that theory. But how do we use observations to study how the universe will end? To explain this, we have to go back to Edwin Hubble. Remember Hubble's law? This was the equation showing us that objects that are further away from us are moving away from us at a greater speed. Hubble and his contemporaries, including Georges Lemaitre, recognized this fact as a sign of an expanding universe. Measuring h-0, the Hubble constant, a number telling us how fast the universe is expanding, is a crucial puzzle piece in the math of how the universe is expanding. In earlier programs, we heard about the many observational tools that astronomers can use for measuring the Hubble constant. One popular method uses a special type of supernova produced when a white dwarf, the leftover dead core of a star like our Sun, explodes. Astronomers knew how bright explosions like these should be, which made white dwarf supernova excellent standard candles. By comparing a supernova's apparent brightness to its expected brightness, and carefully accounting for complicating factors like dust, observers could measure how far away that supernova was. These supernovae happened all over our universe, sometimes in very distant galaxies, and by the early 1990s, two different research teams were racing to find even more distant supernovae, so that they could measure their distances and speeds. By comparing the supernova's distance to how fast it is moving away from us, astronomers could then very carefully test Hubble's law and see whether this observed expansion was staying constant, slowing down or speeding up. One research team was created by Saul Perlmutter at Lawrence Berkeley National Laboratory. The other was founded by Brian Schmidt and Nicholas Sundzetsv. Together the teams included dozens of scientists from all over the world. Working separately for many years, the two teams both reached the same surprising conclusion early in 1998. The fastest moving supernovae were even further away than they had expected. The universe's expansion was accelerating. To understand what this means, we need to go back to the idea of a flat universe. We began by talking about three ways that the universe could end: a runaway expansion that would rip the universe apart, a slowdown and ultimately reversal that would end in the universe collapsing in a big crunch, or a slow and gradual expansion that would slowly and gradually let the universe expand and cool into nothing. These three models are the open, closed and flat models of the universe, and they're often described with something called the density parameter, or omega. An omega smaller than 1 gives us a universe with a swooping curved geometry, shaped like a bowl or a saddle. A universe like that would expand forever, potentially ripping itself apart. An omega bigger than 1 would give us a universal geometry similar to a sphere. Its internal gravity would eventually slow down and reverse the expansion, giving us our big crunch. However, an omega exactly 1 would give us a universe with a nice neat flat geometry. Observations of the cosmic microwave background, the same observations that caught Robert Dicke's attention and inspired Alan Guth to come up with the theory of inflation, have shown us that the value of omega looks to be a practically perfect 1, indicating a flat universe. An omega of 1 tells us exactly how much matter and energy there is in the whole universe, but what that matter and energy looks like is a more complicated question. We know that some fraction of the universe is made up of matter that experiences gravitational attraction, but this doesn't account for all the matter and energy in the universe. The rest, well, we're not quite sure what it is. In mathematical equations it's referred to as the cosmological constant. It's also sometimes referred to as dark energy. Despite the name, dark energy is very different from dark matter. Dark matter is a form of matter that exerts a clear gravitational influence but doesn't interact with light in any way. Dark energy's name doesn't come from how it interacts with light, it comes from how mysterious it is. We think it's a form of energy that helps to drive and accelerate the expansion of the universe, but understanding what it is, how much of it there is and what it does to the universe is still a puzzle. This is where the supernova research teams come in. By measuring the expansion of the universe and comparing them to predictions of how a flat universe with an omega of 1 should look, they converged on a solution. Their observations agreed extremely well with a universe that contained both matter and dark energy. Combining these supernova observations with our studies of distant galaxies and the cosmic microwave background, the teams arrived at a final set of numbers. Adding up to an omega of 1, about 32% of the universe is composed of matter. 5% of that is normal matter, while the other 27% is the much more abundant dark matter. The remaining value discovered by these observations give us a universe that is 68% dark energy. The supernova data earned 3 team members a Nobel Prize just 13 years later, in 2011, awarded to team leaders Saul Perlmutter and Brian Schmidt, as well as Adam Rees, the team member who had led the first peer-reviewed paper presenting this discovery. There's a lot to take in here. Curvy, spherical and flat universe geometries, exploding stars, faint microwave signals, dark matter and dark energy. Cosmology is exactly what it sounds like, the study of the whole cosmos. Researchers trying to explain where the universe is coming from and where it's going to have to account for, well, everything in the universe, from dust to dark matter to gravitational ripples. Still, thanks to decades of meticulous observations, we now think that we know where the universe is headed. Beginning with the Big Bang and followed by Alan Gough's brief but crucial period of inflation, today we see a flat universe that's not only expanding but has an expansion that is speeding up thanks to dark energy. So, what does this mean for how the universe will end? We're still not quite sure. Based on what we know now, most astrophysicists agree the universe will keep expanding forever. This could give us a universe that slowly drifts apart, eventually making it impossible for stars to form. As the stars wink out and the material in the universe spreads further and further apart and cools off, we're eventually left with a dark, frigid, motionless universe. This scenario is sometimes referred to as heat death, or the Big Freeze. Another possibility is the Big Rip, which imagines a steady increase in the universe's expansion that pulls apart galaxies, stars, planets, and eventually even splits up atoms into elementary particles. Whatever the scenario, our best theories all maintain that the end of the universe is coming in 20 billion to 200 billion years. The end of the universe may seem impossibly far away, and we certainly aren't able to wait around and see what happens. This, once again, is why observations and theories are so important. As we build our theories of how the universe begins and ends, and develop new ways to test them, we keep coming closer to answering our big fundamental questions. Where exactly did the universe come from? How did it start? How did it expand so quickly? And how does it look so perfect and uniform today? And based on what we see around us, how do we think it will end? This program brings us to the end of part 1 of this series. Over the last 10 programs we've followed how various heroes of astronomy, both individuals and teams, have shaped our understanding of the universe. These numerous heroines and heroes untangled the mysteries of stars and discovered dark matter. They mapped the expansion of the universe, observed its earliest moments and developed theories to explain its beginning and end. And they built the telescopes that made it all happen. Next we'll move into part 2, studying the physical and energetic extremes of the universe, some of the most brain-bending extremes of astronomy, and the pioneers and heroes from Albert Einstein to the enormous team that discovered gravitational waves that helped make these discoveries possible.